Ladies and gentlemen, hello and welcome, coming to you once again, not quite live from One Take Studios, where today we are talking about systems of non-linear functions, which is kind of crazy because usually algebra is spending a lot of time with systems of equations and they are specifically linear. So today we are talking non-linear. I don't know about you, but that doesn't look like it should be a word. It actually is. Doesn't even need a hyphen or anything. Now, a little bit of a review, walking down memory lane for a second. If we do have linear equations, and we're talking about systems of equations, I love the visual on these because to me it really pulls together the understanding of what's happening. If I have two lines and they cross each other and I'm looking for, where is my solution? How do I solve a system of two, or it could be more equations? What I'm looking for is where is the one point where there is one ordered pair that's going to work for both lines at the same time. And so the point of intersection is it. All right, in this case, we've got one point that's going to work, and that's that one point of intersection. That's going to be the solution that I'm trying to hunt down through one form or another. If I have lines, of course, they don't always cross each other. Maybe they are parallel. I wrote the word parallel just because I know that my lines aren't perfect, so sorry. If they never cross each other, where is the one point or more than one points that works for both lines? I'm not going to find them. So it's entirely possible that there would be no solution to a system of equations. Of course, with lines, it is possible to also end up with identical lines in the exact same place, in which case there's infinitely many solutions. But with where we're headed, it's going to be more likely that we've got a point or two, and then it is also possible to have no solution. So the idea being, looking at the visual, wherever they cross, that's where my answers are going to be. So what does that mean for nonlinear? It means that wherever they cross, that's where the answers are going to be. So we can have lines mixed with parabolas, mixed with travoltas, sorry, that's what I call cubic stuff, quartics, exponentials, hyperbolas, you name it. If we can graph it, and we can graph more than one thing on the same coordinate plane, we can have a system of equations and we can find where the solutions would be. And that's going to be wherever the graphs intersect, all right? So we are looking for intersections more than anything else. Intersections, there we go. That is where our solution is going to be. Now, because we have some strange shapes here, it's possible they could cross at 1 point, they could cross at 2 points, they could cross at 4 points, and it is also possible to have two graphs that never intersect at all. So again, I like the graphing. I think it's a good visual for what's happening, but there are algebraic methods here as well. For linear equation systems, we're talking there's graphing, there's substitution, there's combination methods. If you want to get into matrices, you can do something there too. With these, I think what you're going to see probably more than anything else, although there's other options out there, I think you're going to find graphing to be helpful, and I think you're going to find substitutions to be helpful. So I'm going to walk you through one example that is on the complicated side just to make sure we cover bases and then kind of turn it loose, because that's it, ladies and gentlemen. If you can find the intersections, you can find the solutions. That's it. So the equation or the system of equations that I've got for you today is just peachy delightful here. All right, so here's our system. X plus xy equals -2, and x times y equals -6. Not linear, quite frankly, not even on this list. Ladies and gentlemen, these are hyperbolas. And so I want to walk you through two methods so that you can compare them. You can see what you like. Again, most people think, I think graphing is going to be really good. Well, hold off on that thought and wait till you make up your mind. If I'm going to graph this on a lot of calculators, I do need to have y by itself. So even graphing might take a little bit of work to get the y by itself. If I've got x plus xy equals -2, I can subtract x. So I've got xy equals -2 minus x. Divide by x, y is equal to, that's going to be -2 minus x all over x. And quite frankly, I can put it in the calculator like that, and it'll take it. I may want to use parentheses here to put this together to show that I'm dividing the whole thing by x, but it will absolutely work. And then my other equation's a little bit easier to access. X times y equals -6. If I want to get that y by itself, I just have to divide by the x. So we're talking -6 over x. So again, I may need to do a little bit of work, even if I'm graphing, to get these things in a calculator. And let me show you what we have, all right? Here is my graphing screen. As soon as, there it is. All right, so isn't that lovely? Ah, goodness gracious. There is one obvious intersection in this screen, but you do want to be careful because anytime you're working with graphs, especially things that go to weird places, is it going to cross more than once? Is there a possibility that you're going to have an intersection off of your screen someplace that you really need to be looking for? Yeah, that's absolutely a possibility. So not knowing for sure if these intersect in more than one place, I might need to do some zooming out. I might need to just kind of play around with it a little bit. But I can see one definite spot here. So let's go after that first. I don't know how familiar you are with this. I'm going to go with my menu because everything fun and exciting is in the menu. And I would like to analyze my graph. One of the things I can do is I can ask it to analyze an intersection, which is oh so wonderful. So I'm going to put this, notice it says lower bound in the corner. I'm going to go to the lower bound to the left of the intersection. And I'm going to hit enter. And then I'm going to go upper bound. I'm going to go to the right of the intersection, and I'm going to hit enter. And lo and behold, the calculator very kindly says, hey, 4, negative 1.5 is where these two intersect. So what does that mean? That means that 4, negative 1.5 is my solution. Not one number, not the other, but the two of them together as an ordered pair. That is the one point that I can plug into both equations and have it work for both of them at the same time. Just to be on the safe side, I may want to zoom out a little bit. Let's just take a look at that, shall we? Zoom and zoom out. And from the center, why not? There we go. Whew. You know what? The way these are set up, if you know anything about asymptotes, I'd say that these things are approaching the asymptotes, but it doesn't really look like the two graphs are going to cross each other again. So I think it's pretty safe to say that that one point, that's going to be our only intersection. So here's what I like about the algebraic portion of things. So let's switch screens again, shall we? I'm going to go back here. There we go. So through graphing, we can analyze the intersection. We can find it. We have an answer. Awesome. If I use substitution, algebraically, I can often tell a little bit more easily sometimes than on the graph as to whether or not I've got multiple solutions. Now, substitution, for some of you might say, all right, well, I'm going to take one of my equations, get x by itself or get y by itself, and plug it into the other equation. And if you like that, great, go for it. I'm going to encourage you to open your brain a little bit, please. X plus xy equals negative 2, correct? And xy equals negative 6. If you understand what the purpose is of substitution is to get down to one variable, and you keep your eyes peeled, you might see something really useful. I don't actually have to get x by itself or y by itself to plug into this equation. I could, but I don't have to. What does this say? This says xy. What does xy equal to? Negative 6. I can just make that substitution right there. X plus replacing the xy with the negative 6. So actually maybe I go with minus 6 instead of a plus. So x minus 6 equals negative 2. What did this achieve? I no longer have an equation with an x and a y. I just have x. And that's the whole point of substitution, is to get it down to the point that you have one variable and one variable only, which we've achieved. So even typical algebraic methods, keep your eyes open. You might find something really useful. If I add 6 here, I get x equals 4. Oh, lo and behold, hey, x equals 4. That's kind of nice to know. And then, again, I can't stop here. I have to understand that my solution is going to be an ordered pair or ordered pairs if I have them. And so that x by itself is not enough. I have to go back for the y. And again, this is pretty easy to do right here. So let's say I go back to this guy and say, all right, I know that I've got 4 in place of x, so 4y has to equal negative 6. Just divide. Dividing by 4, dividing by 4, a little bit of a cleanup on aisle 4 here. This is going to be 6 over 4, which is 3/2, which is negative 1.5. And lo and behold, I get the same answer. And I don't have any crazy quadratics going on here, no reason to suspect multiple answers. So algebraically, I can be pretty sure that that is the only point where on a graph I might have questioned myself as to whether or not there could be more than one answer. So, ladies and gentlemen, think about what it means to solve a system, and then apply it. Look for it in the graph, use substitution, but again, just be aware. Be aware, I guess, more than anything else, because strange things can happen, and it's possible to have more than one solution. Or no solutions. So yeah. Alright. Have fun. Enjoy. Thanks.